Hi everyone, it has been a postdoc from UNH and supervised by Professor Noel Lugas. Here I would like to introduce our recent work. It is about studying the role of successive and interacting CMEs in the acceleration and release of solar energetic particles. This presentation contains 4 parts: the background, the identification of twin CME large SCP events in solar cycle 24, the role of the CME interaction on the particle acceleration and release, and the summaries. SCPs are high energy particles coming from the sun, and they are very important in space science studies and space weather. SCPs are traditionally categorized as impulsive and gradual events. Let's see this figure for a gradual and an impulsive event. Previous studies found that large gradual SCP events are always associated with interplanetary shocks driven by fast and wide coronal mass ejections. Here the large means the ion flux with energy greater than 10 MeV is higher than 10 PFU. And this figure shows a very famous eruption in solar cycle 24 on September 10, 2017, and its associated large SCP observations. Some statistical studies have found there exist correlations between CME properties and SCP peak intensities. For example, the fast CMEs can lead to SCP with high peak intensities, but the relation sometimes shows a high degree of scatter. Let's see this figure. The data points in this figure are not well linearly correlated. So, to interpret this scatter, a scenario of a faster primary CME associated with one or more preceding CMEs was found to be a possibility to account for an enhanced SCP peak intensities. This is a case showing the successive CME eruptions and an preconditioning effect of primary preceding CMEs on producing SCPs was proposed by Gopal Swami. In this figure, you can see that both the proton and the electron fluxes of the SCP event are higher in the groups of successive CMEs. And later, we proposed a twin CME scenario. In the twin CME scenario, the preceding CME and primary CME erupt from the same or nearby source region. The preceding CME creates an environment for more efficient particle acceleration with both an excess of seed population and enhanced turbulence level at the front of the primary CME. Extended from the twin CME scenario, some statistical and case studies have shown up. Let's see an example. In 2013, Ding studied all the SCP and the CME events in solar cycle 23. They found that the SCP events with higher peak intensities are always associated with successive CMEs, although their study used the observations from a single viewpoint. And this is a case study about twin CME eruption and the related SCPs. In their study, they found that the particles are released when the primary CME just hits the preceding CME. Today, we can find so many studies on CMEs and SCPs, and we still have 3 questions here, and these 3 questions triggered this work. As for the first one, it is, do successive CMEs in the twin CME events have spatial overlap in the 3D space instead of the projected plan? Thanks to the twin stereo spacecraft, it enables our observations from multiple viewpoints, and it can provide us the information of the CME in 3D space. The second question is, does the introduction of successive CMEs play a role in large SCP event? This was previously raised by Taylor. They found that neither the timing of the pre-CMEs relative to the pri-CMEs, nor the width, speed, or the numbers of the numbers of preceding CMEs correlate with the SCP IP. However, the IP correlates quite well with the two MEV proton background intensities, and this is just shown in this figure. This indicates that the SCP intensities may be controlled by the level of the solar activities. The third question is, what is the association of the acceleration and the release of SCPs with CME-CME interaction? We know that in the twin CME scenario, CMEs have different speeds and time interval. This will lead to different types of CME-CME interaction, and there are 4 types. No interaction, the shock of the pri-CME interacts with the preceding magnetic ejector. The interaction between two ejectors and the interaction between the two CME-driven shock waves. So now, with this question, we start our identification of twin CME event. We found that there exist 41 large SCP events in solar cycle 24, and we used zoological and stereo A and B observations to identify the twin CME event. Let me show how the multiple viewpoints observations can influence our identifications at first. In this middle panel, you can see two CMEs just observed by zoological, and based on these observations, these two CMEs will have spatial overlap in this projected plan. However, after considering the observation from stereo B and from stereo A, you can see that both CMEs are propagating along two different propagation directions, and they won't be interacted with each other in the 3D space. So, we do the identification by using single viewpoints and multiple viewpoint observations. The criteria of the identifications are shown here. The first is the time interval between the two CMEs is less than 9 hours. The second is that the speed and angular width of the preceding CME are higher than 300 km per second and 20 degrees. The third is they will have spatial overlap in the projected plan or in 3D space. We note that here the 3D information in this work is derived by the GCS model, and I will introduce this later. We have 41 events, and this figure just shows the statistical results. At first, based on these observations from single viewpoint, we identified 21 events in twin CME scenario and 20 events in non-twin CME scenario. However, after considering multiple viewpoints, or based on the observations in 3D, we identified 11 events in twin CME scenario and 30 events in non-twin CME scenario. The percentage decreases from 51 to 27. And in this figure, you can see some data points with crosses inside. This indicates that the identifications by 2D or 3D observations are different. And also, based on this figure, you could find that the groups within twin CME scenario, they will have relatively higher SCP peak intensities, and we also found there exist correlations between the SCP peak intensities and the CME 3D speed. We then studied the role of the CME interaction on the particle acceleration and the release. As for the CME 3D information, we used the graduated cylindrical shell model to fit the CME propagation direction, the angular width, and finally derive its speed. This model assumes CMEs have fluxual structure, and this figure just shows the reconstructed result of the primary CME and preceding CME. The particle acceleration is estimated by the type 2 radial burst because type 2 radial bursts are thought to be generated by the CME-driven shock. As for the particle release time, we use the velocity dispersion analysis. VDA assumes the first arrival particles with different energies are released at the same time near the sun and propagate along the same path length. And this in this part just shows the VDA result of this large SCP event. And in total, this figure just shows the relationship. Let me describe this figure. The black and the green lines are related to the leading edge and the trailing edge of the preceding CME. Here the leading edge is the front, and the trailing edge is the tail of the circular main part. The red line refers to the leading edge of the primary CME, and the orange one refers to the primary front along the propagation direction of the preceding CME, because we know that both CMEs can't always propagate along the same direction. And this blue dotted line indicates the offset time of the type 2 radial burst, and this black line indicates the particle release time. We can see that the CME-CME interaction starts before the particle acceleration and release. So it means that when the particles are accelerated and released, there have been meaningful CME-CME interaction. We then perform the similar analysis to the left time event and get the result in this figure. We then focus on the interaction time and the particle acceleration and the following release. Let's use this figure to illustrate the results. In this figure, the gray region indicates the region of the preceding CME, and this is the trailing edge, and this is the leading edge of the preceding CME. The normalized distance is calculated by these two equations, and it shows a relative position between the primary CME and the preceding CME. So in general, if the primary CME can't hit the preceding CME, the data point will lie in this part. If they have interaction, the data point will lie in this part, or even exceed this right boundary. So based on this figure, we found that for 6-of-11 event, the primary CME is far away from catching up with the preceding CME when the particles are released. Okay, let me describe another information in this figure. The horizontal bar, the horizontal length, the left end of this horizontal is related to the offset time of the type 2 radial burst, and the data point here is related to the particle release time. And as for these 6 events, the primary CME is far away from catching up with the preceding CME when the particles are released or even accelerated. But SCP events will have a relative higher peak intensity if the particles are released at the time when the CMEs are meaningfully interacted or close to each other. So let's see these 5 cases. So finally, we go to the summary. We study large SCP events in solar cycle 24 by the observations from multiple viewpoints and found that the multiple viewpoint observations will lead to more precise identification of the twin CME event. We then investigate acceleration and release of a particle for all potential instances of CME-CME interaction in the 3D space and found that the efficient acceleration and the following release of SCP events, SCPs, do not require a meaningful interaction between CMEs, but SCP peak intensity is significantly higher in the events in which the primary CME is closest to impacting the preceding CME. This indicates that the potential for the increased seed populations or more enhanced turbulence levels occurring closer to the preceding CME. And following these findings, we raise another question, which is how long the seed particles can exist after the passing of the preceding CME, and this should be analyzed in the future. Okay, thank you. And if you are interested in this work, please refer to our paper in 2000 and